So we'll be talking about presenting some evidence or result from empirical research that indicates a new paradigm, and the new paradigm relates to the nature of the greenhouse effect itself. We will be presenting, I'll talk about how we came to this relationship and what the implications of that relationship is. Starting here is a word of wisdom from a person who lived around the turn of the century in Scotland, and he was not a scientist, but what he said I think very much applies to what we're talking about. In order to advance science, we really need to be able to have open mind. Next. So our names are Ned Nikolov and Carl Zeller. We are from Colorado, from the beautiful state of Colorado in the States. We're independent researchers, and we do not belong to any organization, political or otherwise. And our stance has been that science has to be impartial, and we are willing to support any policy, any politics that is in line with the scientific evidence. So whatever that is. So I want to say this up front, we don't have any political affiliation, we'll probably never will in the near future. So the information I'll be presenting here will allow you to answer this question. You can think about this question while the presentation goes on. And the question is, what do a diesel engine and Earth's climate system have in common? The premise that the thing that put us on the path of doing this research were a number of apparent inconsistencies between observations and theory. And so our premise was in the very beginning the idea that the temperature of Earth should be determined by the same factors that are controlling the temperature distribution across planets of the solar system. In other words, if we do analysis of the data that currently exists in the solar system, and we derive a relationship, this relationship should be able to give us the main drivers that can explain the variation of climate on Earth over a long period of time. So if this premise is true, then the hypothesis that we put forward is that a model should exist, a general model should exist that can explain the variation of temperature across the planets in the solar system with a common set of drivers. To do this, we have looked at the solar system and have selected a number of bodies for analysis. And our analysis was based on three criteria. Number one, we were looking for bodies that have a hard surface, because we want to assess the temperature of the surface temperature of planets, so that implies the availability of the hard surface. Number two, the planets that we work with should have good data that are based on actual observations and high quality observations. And number three, the planets should span a very broad range of conditions. So here we have 6 bodies starting from Venus, Earth, Moon, Mars, Titan, which is a satellite of Saturn, and Triton, a satellite of Neptune. In terms of conditions, you can see that they span a range from, in terms of solar radiation reaching each of the planets, spanning the range from about 2,600 watts per square meter down to 1.5 watts per square meter. In terms of albedo, the variation is from about 0.14 for the Moon to about 0.90 for Venus. The atmospheric composition and the total pressure is equally stunningly wide in terms of variation. So we have a body like the Moon that has no greenhouse gases to Venus that has over 96% of greenhouse gases, and so forth. So this is a really broad environments that represent a very broad range of conditions. So our analysis was based on a technique called dimensional analysis, which has been used in engineering in the past. It's a classical method. The technique basically means what it implies, that the derivation of physically meaningful relationships from empirical data without a reference to any theory. That's the part of it. In the old days, when in fluid mechanics and other sciences where a process was not known well, you have a bunch of data, you want to make sense of them, you actually apply this method to see if there is any relationships that are meaningful that you can use. By the way, everything that we call now fundamental science and theoretical science, things like the Planck constant, the ideal gas constant, the gravitational constant, they're all based on measurements and fitting data. So the information that's now in our theoretical science, it came originally from empirical measurements. So we're applying this approach, but on a planetary scale, not in a laboratory as was done in the past, in the beginning of the 20th century when the foundations of physics were placed. So the dimensional analysis, the key feature of the dimensional analysis is that it works by reducing the units that we use for variables that we're investigating, reducing them to a common set of fundamental dimensions. Majority of the units, or majority of the variables in physics and parameters, they can be reduced to 4 fundamental dimensions. Those are absolute temperature, identified here with theta, mass, m, l, length, and t, time. And for example, what I mean by that, speed, for example, is measured in, you can measure it in meter per second, you can measure it in miles per hour, but fundamentally, speed is a length by unit time, or length divided by time. In a similar fashion, for example, here the solar radiation that is measured in watts per square meter, when you do the decomposition to fundamental dimensions, you actually end up that the watts per square meter equals mass divided by time cubed, something that is counterintuitive, and a lot of people don't realize that. And so, but with the same way, by the same token, you can see here relationships between variables that are otherwise not obvious. For example, the flux, energy flux here, being with those units of mass per time cubed, you obtain this unit by multiplying a pressure times the speed. So if you see the pressure has units of mass divided by length divided by time squared, if you multiply this by length by time, you actually get this unit. So basically, by doing dimensional analysis, you realize that watts per square meter is a pressure times the speed of the moving particles. So this is a list of variables that we have worked with, and you have here temperature, you have the solar radiation reaching to the planet, to the top of the atmosphere of the planet. We have something called reference temperature, which in our case is the temperature of the planet without atmosphere. So any planet that we studied that has atmosphere, we also calculate the temperature for that planet without the atmosphere, and we'll get to that in a little bit later. Then we have the pressure and density, not only total pressure and density of the atmosphere, but also partial pressure and partial density of greenhouse gases. So the result from the dimensional analysis was 12 models. Once we got the non-dimensional numbers that are produced by the dimensional analysis, we have to find relationships. So here those 12 models have been explored with a curve that is a common equation but has different shape because the regressions are different. And you cannot see very well here, but you have on the y-axis you have always a temperature ratio, which is the ratio of the planet to the temperature of the planet without atmosphere. And then on the x-axis you have different non-dimensional numbers that include the density of the greenhouse gases, the partial pressure of greenhouse gases, the absolute density, the absolute pressure of the atmosphere. And so out of all these models, the only one that actually produced a very tight relationship is this number 12. And this is the relationship between this temperature ratio, which we call it the relative temperature, you can call it, or because it's a ratio of temperature to the temperature with no atmosphere, it basically quantifies the thermal effect of the atmosphere, so we call it atmospheric thermal enhancement. This is another word for the greenhouse effect, which we think is more accurate than the current word the current term that's being used. So this is a log-log scale, and I can see the correlation is almost 1. The error is very small. And by the way, this model is about 20 times more accurate than the second best model, which happened to be number 1 up here and behind. So there is a big difference between this model, this fit, and all the other options. Here we have the curve that is after the anti-log, and we have the actual equation. And here we see the atmospheric thermal effect, which is on the y-axis, given with the temperature ratio, as a function of total pressure. And you see that all the planets, they line up actually in a very nice way. The only little exception is Titan. It's very close to the curve, but the temperature of Titan was uncertain, so we have excluded actually Titan from the regression. On the bottom, you see the equation. The T sub Na is the equivalent to temperature without the atmosphere. We have a handout for that. You can read about that more. It was based on work published in 2014 by Volokin and Velez in Springer Plus. So this is a whole topic by itself. We can talk about how this is done, but we don't have the time right now, and maybe if we have discussion, if people are interested, I'll be happy to elaborate further. Okay, next. This thing is not very responsive. Okay, so here we're showing the absolute accuracy of the model. And as you can see, for all the planets but Titan, the accuracy of the curve that reproduces the current observed temperature is less than 0.17 degrees. I mean, this is engineering accuracy. This is not ecological or climatological accuracy. We're talking about something else here. So in order to test if this relationship actually it's viable, there is a thing called statistical robustness, and that means that if you change a number of parameters, or the number of data points, or you have a new data set and you derive another regression line, you can compare it to the original one and see how far it is from the original one. So here, this is exactly what we have done. The solid line is the original equation that includes all the bodies. And the dashed line is a new regression equation that has where we have removed the Earth and Titan from the set of data that is used to create the regression. And the idea was how close the new regression line can predict the temperature of Earth and Titan. And as you see here, they are very close to the line. In fact, the new line predicts the temperature of Earth with an accuracy of 99.6%, which is within 1 degree. Now again, to repeat that, the new regression line was derived by having only Venus, Moon, Mars, Triton, Mars and Triton in the regression line. So Titan and Earth were excluded. And yet, having those worlds that have nothing to do with Earth, very different, right? The Earth's temperature was predicted by this line, but by this curve, with an accuracy of 99.6%. So that tells you that Earth is a part of a cosmic continuum that is described by this curve. Now, I didn't mention, but we're talking here about long-term average temperatures. A long-term meaning at least 30 years average. We're not talking about specific year or specific decade. We're talking long-term equilibrium average temperature. So you can look at this curve and think about this like the backbone or the baseline of what determines climate. Because temperature is has a direct relationship with kinetic energy, which determines everything. So this is a temperature ratio that we have here is basically the ratio of energies. So then the question is, how we can explain this in terms of physical terms, this relationship. Is this an accident? Is this a statistical fluke? Or what is it? So, if we go back to the basics of foundation of physics, or specifically in thermodynamics, we find out that temperature is proportional to the internal kinetic energy. This is of any system. We have a handout here for that one. Number 2, people, if you want to look at that. Second, the energy, the kinetic energy, by definition, is a force applied over a distance, which is joule. 1 joule equals Newton times the distance meters. Thirdly, pressure itself is a force per unit area, so that the product of pressure times volume, this comes from the gas law, equals energy. This is something that we have all to be reminded about, because in climate science it's quite often forgotten that P times V is the kinetic energy of the atmosphere. And then the 3 points above, they give us a conclusion that the energy, the kinetic energy and temperature cannot exist without a force. That's a physical fact, meaning that in any system where there's kinetic energy and temperature, you find some form of pressure. What do I mean? People say, what about radiation? Well, from the dimensional analysis, as I mentioned before, the energy flux, which is watts per square meter, this refers to any energy flux, radiation included, is the pressure times the speed of the moving particles. So, how many of you knew that radiative flux equals photon pressure times the speed of light? That the light has pressure. Everybody knew about that? Good. So, this is known to NASA, the satellite that they send in orbit. If they don't do a correction for that, for the effect of light as a pressure on the satellite, they drift off orbit. So here's the equation that any radiative flux is photon pressure times the speed of light. Since the speed of light is constant in any medium, that means that changing the intensity of radiation within a given medium, we're talking about changing fluctuating the pressure of photons, essentially. So that gives an opportunity here to express a very well-known law, the Stefan Boltzmann law, to express it in terms of photon pressure. How you do that? On the right-hand side, you see the temperature given as a radiation divided by the Stefan Boltzmann constant and the fourth root of that. And then if you divide both sides of this equation by some constants, like for example the temperature of this space, which happened to be, this is irreducible temperature of space, which has happened to be about 2.7 Kelvin. On the temperature end, you divide this by T sub C, and on the radiation end, you divide the radiation by the equivalent or the causative agent of this cosmic temperature, which is the cosmic microwave background radiation, which happened to be a very small number. So you get this expression, a temperature ratio equals the fourth root of a radiation ratio. Well, further, if you express the radiation in terms of photon pressure, come on, you get an expression that gives you the temperature ratio as a function of the ratio of pressures. Now, what is the shape of this relationship? You know, we can plot this, and here is the shape of this relationship. This is a new form, a new way of expressing the Stefan Boltzmann law. Okay? Well, how this compares with the relationship that we have just derived. Oops, I went too fast. You can see that the shapes of those curves are very similar. They belong to different systems, so therefore the magnitude of the x and y axis are quite different. But the shape is very similar, and the other commonality is that in both cases we have a temperature ratio related to a pressure ratio. We have a third system that's called adiabatic heating, or the Poisson formula, that gives us the rate of change in temperature with pressure alone. And here you have the third curve, which is eerily similar to the other two curves. So here we have a very strong qualitative resemblance between all the curves, right? So that tells you that there is something physical about this relationship at the very end that we have derived from the planet, that it's not a random event. Okay, so the conclusion from this is that this relationship that we just derived, it has a macro-level physical reality to it. Now, we have went through a number of characteristics of this curve, number one being the high accuracy that we saw, number two is a very broad range of validity, number three is the statistical robustness, and number four, it is physically meaningful. So therefore, as a conclusion, we can say that this relationship appears to describe a micro-level thermodynamic feature of the planetary atmospheres heretofore unbeknown to science. What is the implication of that relationship? The implication is that the physical nature of the so-called greenhouse effect is actually a pressure-induced thermal enhancement, which is independent of atmospheric composition. Because we have the atmospheric composition with partial pressure and so forth in our analysis and did not produce any meaningful relationship. Now, you have to remember this is across a broad range of conditions, much broader than occurs on Earth, and we're talking about long-term equilibrium temperature. So, to finish with the question that we started with, what do a diesel engine and Earth's climate system have in common? You can figure it out. Well, the answer is that both systems rise the internal temperature of the system through gas compression. So that's a new paradigm. So basically what we're saying here, that there has been a confusion that has been going on for 190 years about the physical nature of the greenhouse effect being a radiative phenomenon. It is not a radiative phenomenon. It is actually a phenomenon caused by pressure. It's a pressure-induced thermal enhancement. But it's kind of hidden. If you don't see that until actually you do the analysis, you know, to the planets. And the way it started back in 1824 with Joseph Fourier, he just expressed the notion, it looks like the atmosphere works like a blanket. And it stops the cooling, or it slows down the cooling. In fact, it's not, there is no stopping or slowing down of the cooling. It's just an enhancement of the energy that's coming from the sun, because the energy that's coming from the sun is also a result of photon pressure, you can say. And this energy being absorbed by the Earth, it is being enhanced by the pressure of the atmosphere on Earth, because it doesn't matter if it's a photon pressure or gas pressure, pressure always changes the temperature. So that's the fundamental new aspect. Thank you.